We talked quite a bit in the last lesson about solving quadratic equations using the tool of square roots. And while I was working through those examples, I pointed out that we wanted things to look as much like perfect squares as we could in order to use that square root tool. We even looked at one example which was written in a very special way so that the square roots worked really well. It was the equation x minus 3 squared minus 49 equals 0. I pointed out that this was a rewriting of the equation x squared minus 6x minus 40 equals 0, which certainly does not look like an equation on which we could have used the square roots tool. Now I hope that some of you were wondering, how in the world did he know to rewrite x squared minus 6x minus 40 equals 0 in this prettier form, x minus 3 squared minus 49 equals 0? Well, that question is exactly what motivates this lesson. The trick, or method, as I like to call it, is known as completing the square. And by using completing the square, I can rewrite such equations so that the pieces look like perfect squares. Actually, completing the square is used for more than just solving quadratic equations. It's really a way to rewrite a quadratic equation in a very special form, which tells us the location of the vertex of the corresponding parabola. Let me show you what I mean with a quick motivational example. I want us to determine the smallest value of the quadratic function f of x equals x squared plus 6x plus 42. So first, let me make sure that we understand what I'm asking for. The question is, what is the smallest output value of this function f of x? Or I could say it this way, what's the smallest y value of the function f of x? One way to get a feel for this is to just plug in a whole bunch of numbers for x and see what the different y values are. This will not tell us exactly what the smallest value is, but it should give us a hint as to what it's going to be. So let's do this and see what happens. I'm going to plug in a whole bunch of numbers for x, and I'm going to see what I get back as y values from the rule for f of x. If I plug in -6 and then do the arithmetic, I'm going to get 42 back as the y value. If I plug in -5, I would get 37 back. If I plug in -4, I would get 34 back. And notice that these numbers are getting smaller. Remember, I want the smallest y value possible. When I plug in -3 for x, I get 33 back for f of x. That's a little bit smaller. And when I plug in -2, I get back to 34. And when I plug in -1, I get 37 back as the function value or output value. When I plug in 0, I get 42, which is even bigger. And when I plug in 1, I get 49. So it looks like, at least according to the numbers I plugged in, that the lowest y value is somewhere around 33. And that occurred when x equaled -3. But how can I be certain that this is the smallest output value for the function f of x? Well, believe it or not, the answer can be found exactly by using this completing the square. So here's how it works. I'm going to start by looking at the first part of the equation, and by first part of the equation I mean the x squared plus the 6x. Now here's a question that we need to ask in order to do this completing the square. What constant would we need to add to x squared plus 6x so that I end up with a perfect square? In other words, I want a number, let's call it a, so that when I write x squared plus 6x plus a, I can factor that into a perfect square. In this case, that value of a would need to be 9, and that's because x squared plus 6x plus 9 equals x plus 3 times x plus 3 when I factor, and that is x plus 3 squared, and that's a perfect square. Now that's really helpful to see. Now let me go back to my original function, which was x squared plus 6x plus the 42. Notice that I can add and subtract 9 if I want to, and rewrite this in what looks like a complicated way at first, but just bear with me. I would have x squared plus 6x plus 9 minus 9 plus 42. Of course, the plus 9 minus 9 is sort of like adding 0, which doesn't do anything. But now I can regroup these numbers in an intelligent way and rewrite it with a little set of parentheses this way. X squared plus 6x plus 9 in parentheses minus the other 9 plus 42. And if I simplify the negative 9 plus 42, I have x plus 3 squared plus 33. Notice that what I've done now is written a part of this with a square plus an extra term that's hanging off on the end, the plus 33. I have successfully done what we call completing the square. But you might say to me, so what? Who cares? Well, here's why this is important. The first part of this new expression, x plus 3 squared, is never negative as long as we're plugging in a real number. And we are plugging in just real numbers here. Why? Because if you plug in a real number for x and you square, no matter what you plug in, that part will have to either be 0 or positive. And so here's what I now know. X plus 3 squared plus 33 is greater than or equal to 0 plus 33 because the x plus 3 squared part is always greater than or equal to 0 when I plug in a real number. And 0 plus 33 is 33. So no matter what we allow x to be, we know that this function is always greater than or equal to 33. Therefore, the smallest value for y that we can have for our function is 33. And this is proof of the conjecture, the guess that we made earlier, that 33 is the smallest value the function can take on. Now, we can also say the same fact in the language of the vertex of a parabola. So here's what we mean by that. This function that we started with is a quadratic function. And that means that its graph is either a parabola that's going up or a parabola that's going down. In this case, the number in front of the x squared is positive. It's positive 1. And that means the graph we have is a parabola with the ends going up. What is this 33? This 33 is the y value of the point that's the vertex of the parabola. In fact, I can actually take this one step further. We know both of the coordinates of the vertex thanks to the way I rewrote this problem with completing the square. Remember, I had x plus 3 squared plus 33. The 33 part is the y coordinate of the vertex, and believe it or not, the x plus 3 tells me that the x coordinate of the vertex is negative 3. And that pattern continues on even if you look at other quadratic functions that have been rewritten with completing the square. For example, the vertex of the parabola that can be drawn from the equation y equals x minus 5 squared plus 10 is just 5 comma 10. The vertex of the parabola from x minus 3 squared minus 7 is 3 comma negative 7. The vertex from the parabola y equals x plus 1 squared plus 8 is negative 1 comma 8. And lastly, the vertex of the parabola y equals x plus 2 squared minus 17 is negative 2 comma negative 17. Basically, the x coordinate is the opposite of the number inside the squared term, and the y coordinate is the number that's outside the squared term. So we see that this completing the square is actually extremely helpful if we're trying to find the vertex of any parabola. That's just one reason to use completing the square, but it's a very, very important one. So we now know the main object of this lesson. I want to be able to rewrite quadratic functions so that they look like x plus a squared plus c, or possibly negative x plus a squared plus c, where a and c are just some real numbers. Once we've been able to rewrite any quadratic function that way, we can interpret the information that we're given to tell us a whole bunch about the function and also about the parabola and its vertex, which are the graph of that function. Now, let's see if you can complete the square on an example on your own, just for a moment, and then we'll work it together and see how you did. Complete the square for the following quadratic function. F of x equals x squared minus 10x minus 30. Okay, as with the previous example, I want to determine the coefficient that I would need in order to complete the square if I'm going to have x squared minus 10x plus something. Guess what? There's actually a recipe for finding that number. Here's what you do. You take the coefficient that's in front of the x to the first term, and you ignore the sign in front of it. You don't even need the sign. You just need the number in front of the x to the first term. In this example, that's 10. You always divide that number by 2. It's always dividing by 2. And that gives me 5. And then I square that 5 to give me 25. So I started with the 10, I divided by 2, and then I squared. And 10 divided by 2 is 5. 5 squared is 25. And that means this. In order to complete the square here, I need to add 25 to the x squared minus 10x. But of course, if I add 25, I need to also subtract 25 so that the overall impact is just 0. And so my original expression becomes the following. X squared minus 10x minus 30 is the same as x squared minus 10x plus 25 minus 25 minus 30. And now if you group those the right way, you'll have x squared minus 10x plus 25 minus 55 on the outside, and that's the same as x minus 5 squared minus 55. And once you've done that, and that's all we were asked to do in this problem, you can actually interpret this even farther. You know that the smallest value that is going to be the output value of f of x equals x squared minus 10x minus 30 is equal to negative 55. That's the negative 55 that was dangling on the end after we rewrote this function using completing the square. Actually, you can say even more. You know that this function will have a graph which is a parabola. You know that the parabola is going up because the number in front of the x squared term is 1. And that means you know the range of this function. The smallest y value you can have is negative 55. And then the function is going to grow up from there all the way to plus infinity, if you want to say it that way. And therefore, the range of this function is from negative 55 up to infinity. Now, let's extend the work we just did in this example to solve an equation. So I think this is a good idea. Solving equations has been of interest to us now for a couple of lessons. So let's talk about how we can use completing the square to help us solve equations. Here's the example I want to look at. Solve the equation x squared minus 10x equals 30. Well, I know that this equation, x squared minus 10x equals 30, is the same as x squared minus 10x minus 30 equals 0. Remember, one of the rules that we often use for solving these things is to move everything to one side. Now, let's use this new equation, or this rewriting of the old equation, x squared minus 10x minus 30, to solve that old equation. Well, wait a minute. You and I just looked at x squared minus 10x minus 30, and we realized that that could be rewritten as x minus 5 squared minus 55. That means that our equation that we're dealing with now can be rewritten this way. X minus 5 squared minus 55 equals 0. And now, look at what you've done. This thing is rewritten so that you don't see any x to the first terms anymore. They're now sort of hiding. And if you think about it for a moment, from the previous lesson, we now know how to finish this problem using square roots. I can now rewrite the equation as x minus 5 squared equals 55 by adding 55 to both sides. And now I can take the square root of both sides. And when I do that, like I did in the previous lesson, I'll have x minus 5 equals plus or minus square root of 55. Remember, when you take the square root of both sides like we just did, you must include that plus or minus. And now you have x minus 5 equals plus or minus square root of 55. You can split that into two equations. X minus 5 equals the square root of 55, or x minus 5 equals the negative of square root of 55. And if you just add 5 to both sides, you'll have your two solutions. They are x equals 5 plus the square root of 55, and x equals 5 minus the square root of 55. And believe it or not, those are the two solutions for that original equation, and the problem is done. And notice that those two solutions were a bit messy. Square root of 55, which doesn't really simplify very well, but those really are the final answers, and both of those are real numbers, so they really were the answers that we wanted. Now, I'd like to transition to a few more examples that demonstrate the different kinds of things that can arise in these sorts of problems where you want to complete the square. So here's the first question. What happens if the coefficient of that middle term, the x to the first term, is odd? Well, let's work through an example where that sort of thing happens. The same recipe works, but the arithmetic can get a bit messy. Here's what we need to do. Solve the equation x squared plus 7x minus 8 equals 0, and let's do so by completing the square. So remember, with completing the square, the first thing you need to do is grab the coefficient of the x to the first term. In this case, it's 7. You're going to have to divide that by 2, and then you have to square. Unfortunately, since 7 is an odd number, the arithmetic is going to get a bit messy, but we can do it. Just let's work it one step at a time. Let's be patient as we work through it. The number that we want to add to x squared plus 7x in order to get a nice square term is going to be 7 divided by 2 and then squared. So I'm going to have 7 over 2, and I'm going to square that number. And if you do that, you have 7 halves times 7 halves, which is 49 fourths. So I need to add and subtract 49 fourths to my original equation in order to continue on. That's going to give me x squared plus 7x plus 49 fourths minus 49 fourths minus 8 equals 0. Doing a bit of that regrouping is going to give me x squared plus 7x plus 49 over 4. I need that together. Minus 49 over 4 minus 8 equals 0. Now the part that I just wrote in parentheses is the same as x plus 7 halves whole thing squared. That's actually the point of doing the completing the square. You get that piece to be a perfect square. You still have minus 49 over 4 minus 8, and then all of that equals 0. Let's get a common denominator for those last two pieces, 49 over 4 and the 8. That common denominator is going to be 4, and that's going to give you x plus 7 halves squared minus 49 over 4 minus 32 over 4 equals 0. And the 49 over 4 with the 32 over 4 are going to combine to give you 81 over 4, so that you'll have x plus 7 squared minus 81 over 4 equals 0. Adding 81 over 4 to both sides gives me x plus 7 halves squared equals 81 over 4. And I've picked the numbers pretty carefully because 81 over 4 is 9 halves squared. And by doing that, it's a hint that I should now use this square root tool that we've talked about before. Once I have x plus 7 halves squared equals 9 halves squared, I can take the square root of both sides and I'll have x plus 7 halves equals plus or minus 9 halves. And that means you have two possibilities. Either x plus 7 halves equals 9 halves, or x plus 7 halves equals negative 9 halves. And now if you subtract the 7 halves from both sides of both of those equations, you'll have x equals 9 halves minus 7 halves, or x equals negative 9 halves minus 7 halves. And if you combine those and simplify, you're going to have x equals 2 over 2, which is 1, or x equals negative 16 over 2, which is negative 8. Now, wait a minute. At the end, we get these two gorgeous solutions, 1 and negative 8. They're just whole numbers, and they're coming from Well, where are they coming from? Because the completing the square looked pretty messy. Well, I kind of took us down a different path. Let me mention, as I have before, that sometimes you can take a different path to get to the same answer. Remember the original problem had x squared plus 7x minus 8. Well, guess what? That actually factors. We could have used that tool from a few lessons ago. X squared plus 7x minus 8 just equals x minus 1 times x plus 8. And that's where the 1 and the negative 8 come from. So, what is my point? Well, if we hadn't been forced down the completing the square route, we could have actually just used factoring. But that's okay. To find the same answer two different ways isn't a problem. In fact, I think it's a great way to confirm that what we did was right. So, what's my point? My point is sometimes completing the square is useful and is the only way that you can actually solve the problem. Sometimes there are other ways, and you want to make sure you're spending the time to think about using the different tools in the right way, because sometimes one tool will get you there a little quicker than another. Okay, now you might be thinking that the arithmetic on these kinds of problems will always be sort of clean, and I can assure you, unfortunately, that it's not always so nice. The example that we just did, where the two final solutions turned out to be whole numbers, worked out simply because that factoring was there. If the factoring had not been there, then the numbers would definitely not have been so friendly at the end. So let me show you another completing the square problem now, which has a slightly different twist. The numbers will still be okay. Sometimes the numbers get really messy. In this case, though, there really is a twist, and so let's talk about it briefly. I want us to solve the equation negative x squared plus 8x equals negative 40. Okay, so what's the twist? Well, notice that I've put a negative sign in front of the x squared term. Oh no, what do? We just stop. Maybe we should just quit. No, don't do that. Why don't you start by multiplying both sides of the equation by a negative 1? If you multiply both sides by negative 1, then whatever equation you end up with will actually have the same solutions as the one you started with. So if you multiply the original equation by negative 1, the left-hand side becomes positive x squared minus 8x, and the right-hand side becomes positive 40, because the negative of negative 40 is positive 40. And that means that the question I just asked you to do is the same as solving this equation, x squared minus 8x equals 40. Why don't you try that first and see what you get? Okay, this time I'm going to use completing the square again. I'm just going to leave that 40 on the right-hand side. I'm allowed to do that. We could move it over, but we don't actually have to. Let's now complete the square using the x squared minus 8x. Okay, what do we need to add to x squared minus 8x to get a perfect square? Well, we take the 8, divide it by 2 to get 4, square that to get 16. It's the same recipe as before. So I need to add 16. But if I add 16, I've got to subtract 16 in order to make everything balance. And that means I'm going to write x squared minus 8x plus 16 minus 16 equals 40. Grouping the plus 16 with those other two terms at the front will actually give me x minus 4 squared minus that extra 16 equals 40. Let's swing that negative 16 to the right-hand side, and I'll have x minus 4 squared equals positive 16 plus 40, which is the same as 56. And now you can take the square root of both sides, and you'll have x minus 4 equals plus or minus square root of 56. Don't forget the plus or minus. And once you've done that, you can split this into two equations. X minus 4 equals square root of 56, or x minus 4 equals the negative square root of 56. And adding 4 to both sides of both of those equations gives me x equals 4 plus the square root of 56, or x equals 4 minus the square root of 56. Now we ought to clean those square roots up just a bit. 56 is the same as 4 times 14. So square root of 56 is square root of 4 times square root of 14, and square root of 4 is 2. And therefore, my two solutions are really x equals 4 plus 2 times the square root of 14, and x equals 4 minus 2 times the square root of 14. Unfortunately, 14 doesn't have any perfect squares in it, so I can't clean that square root up any farther. But those really are my two solutions. 4 plus the 2 times square root of 14, and 4 minus 2 times the square root of 14. Now, let's look at another twist which feels a bit similar to that negative coefficient in front of the x squared term, but it's slightly different. So again, I want you to see all of these different ways that the problems can look. Here's the example I want us to look at. Solve the equation 2x squared minus 12x minus 14 equals 0. Now, notice that I've got that 2 in front of the x squared. This is the first example where I've put a positive number, other than 1, in front of that x squared term. So what do? Well, you don't actually want to start by dividing that 12 that's in the middle, in front of the x term, by 2 and going from there. I know that was sort of the first step we've been looking at, but actually, that first step only works if the thing in front of the x squared is a 1. Right now, the coefficient in front of the x squared is a 2. So the first thing we really ought to do is factor out a 2 from all of the terms on the left-hand side and divide it out. And when I do that, I'm going to have the following. 2 times the quantity, x squared minus 6x minus 7, equals 0. And now I can divide both sides by 2, and I'll have x squared minus 6x minus 7 equals 0. Remember, 0 over 2 equals 0. And now here's the point. The solutions of the original equation are the same as the solutions of this new equation, x squared minus 6x minus 7 equals 0. Fortunately, all the coefficients in that original equation were multiples of 2. So we're still working with integers in this new equation. Even if the original coefficients had not been multiples of 2, it wouldn't have hurt us. We could have still divided out that 2. It's just that the arithmetic would have become much messier. But we could have still divided by that 2, and actually we needed to do that first. Now, can you finish solving this yourself? Solve x squared minus 6x minus 7 equals 0. Okay, here's how I do it. I look at the 6 in front of the x, because I'm going to complete the square. I divide that by 2 to give me 3. I square that, and I get 9. And that means I need to add and subtract 9, and I want to glue the plus 9 over with the x squared minus 6x. We're going to group them that way. And when I do, I'm going to have x squared minus 6x plus 9 grouped together, minus 9 minus 7. The x squared minus 6x plus 9 is the same as x minus 3 squared. By the way, that 3 is 6 over 2. That's where it comes from. And so now I have x minus 3 squared minus 9 minus 7 equals 0, which is the same as x minus 3 squared minus 16 equals 0. And if I add that 16 over to the other side, I have x minus 3 squared equals 16. And now I can pull out the square root tool from the previous lesson, and I take the square root of both sides, and I have x minus 3 equals plus or minus the square root of 16, which is 4. So I really have two equations. X minus 3 equals 4, or x minus 3 equals negative 4, and if I add 3 everywhere, I get x equals 7, or x equals negative 1. Now, you can check that these are the solutions by just plugging them back into the original equation. And we haven't done this together for a while, so let's do it here. The original equation was 2x squared minus 12x minus 14 equals 0. Let's check to see if 7 is a solution. So I plug 7 in everywhere for x, and I have 2 times 7 squared minus 12 times 7 minus 14 equals 0. That's 2 times 49 minus the 12 times 7 minus 14 equals 0. Which is the same as 98 minus 84 minus 14, which is 0. And if you do 98 minus 84 minus 14, you really get 0. So you have 0 equals 0, and that value really was a solution. It really is. Now let's plug in the negative 1. And you have 2 times negative 1 squared minus 12 times negative 1 minus 14 equals 0. That's the same as 2 times positive 1, because negative 1 squared is positive 1, plus 12, because negative 12 times negative 1 is positive 12, minus 14. So you have 2 plus 12 minus 14 equals 0, and of course that means 0 equals 0, because 2 plus 12 is 14. and 14 minus 14 is 0. So those two numbers really were the solutions, and we know that we can check that with no trouble. Well, we've seen this technique known as completing the square now, and we've used it to solve some quadratic equations. We've now built a number of tools, factoring, square roots, and completing the square. But there's another tool I want to show you next time, and that's called the quadratic formula. So next time, we'll talk about that quadratic formula. I'll see you then.